into how to apply AI and ML in the context of cybersecurity. But that being said, I'll start with very basic under the assumption that some of you, and I could see that from the registration data also, that at least there are several folks who do not have a background in AI ML or a thorough background in AI ML. So I'll try to give you a very short primer, a very short exposure to what is AI, what is ML, what are the different techniques available in AI and ML, and how we can potentially use them in the context of cybersecurity. Right? With that as a broad outline, I'll try to maybe start initially with AI ML, and then I'll also jump the gun towards the later part because I'm a researcher at the end of the day, right? So it's always important for us to highlight what are the potential areas of research in this domain. So I'll also try to cover certain aspects of AI and ML, which probably Professor Igor has not planned to cover as part of his presentation. So it will be complementary in some sense to what we're going to have later in the afternoon, right? For those of you who do have a background in AI ML, some of this may sound repetitive, but please bear with me and feel free to contribute. Feel free to ask at any point of time if you have any comments or any suggestions. So these two terms itself are a lot of times used interchangeably. A lot of times we say AI or ML or AI and ML, but they're not the same. In some sense, if you look at it, AI is a very broad term. Like artificial intelligence can encompass many things. One of them is machine learning, but it can also encompass NLP. That's a flavor of the day these days. Natural language processing, for example. A lot of you must be using GPT-based or similar, AI tools. And that is where the differentiation comes. It's not just a machine learning tool; it's an AI tool because you can write in your natural language. It can be in English, it can be in Hindi or any other language, and then the GPT responds, right, in some sense, gives you a logical answer, which is not necessarily only machine learning. So you can have NLP, which is natural language processing. You can have reasoning to a certain extent. You can also have planning done through artificial intelligence. So those are subsets of AI. But for today's session, mostly I'll be focusing on machine learning. And that is why I mentioned in the beginning that our group works at the intersection of wireless communications, machine learning, and sensing. So not necessarily the other aspects of artificial intelligence, right? Within machine learning also, there are several terms that you might have been hearing. People talk about supervised learning, unsupervised learning, reinforcement or dynamic learning, and deep learning. So I'll try to cover them to a certain level of detail. But again, please note, because this is not a course on AI and ML, we can go on and on each of those topics for maybe 5 days, right? There is enough material, there is enough kind of models available, enough type of research that has been done in past 10 years that we can pick a use case and then focus on some of those aspects only, right? Purely from a machine learning perspective. What I'll try to do is maybe give a very brief introduction and then try to motivate how to use it in the context of security or maybe in the context of privacy also in some cases, right? So maybe starting with the first one, which is very commonly used, supervised learning technique. As the name indicates, there is supervision available. What do we mean by supervision here? Essentially, it means that the data that is there, and in our context, for example, we're talking about security. So in security context, we can have a piece of code. We can have a piece of code which is benign, which is safe to run in our software or in our runtime environment. We can also have a malicious code, right? The assumption in supervised learning is we have, and this is again a classification type of approach. We can have parallelly a regression based approach also, right? But I'll only present the classification one in interest of time. Where in classification, essentially what we are trying to do is, for this particular problem statement on the board, we are trying to classify, given a piece of code, is that code benign? Is it safe to run? Or is it a malicious code? And to decide this, we want to train a particular model, a machine learning model. And this process is called as supervised learning because here we are assuming we have sufficient amount of data in terms of labeled data. So we have lots of codes, both benign and malicious type, with the label that it's a benign or a malicious code, right? So the underlying assumption in supervised learning is that we have labeled data set available. Hopefully, larger the amount of data, it correlates sometimes to better performance also, right? And given this data, we are going to train a particular ML model, and I'm going to go into details of some of them as we go forward, right? So for different models, in supervised learning itself. So in different models itself, we will try to train them. So it's the same piece of code. Essentially, you can view an ML model as a piece of code that we will train using this labeled data set. And then this code will try to classify that is it a benign code or is it a malicious code. And we'll try to achieve this in the testing phase. So we have a labeled data set for codes, benign or malicious. And now in the testing phase or the protection phase, we want to use this ML model in the context of security. And now for any unknown code or any new piece of code, we should be able to use this trained model and we should be able to predict, is this unknown code benign or malicious, right? That's a standard architecture for a supervised learning technique. Within this, we can have different types of models. Again, there is a huge amount of literature available there. I'll just give you a glimpse of a couple of very well-known models, right? In what context we can potentially use them from a security perspective. So to begin with, we look at decision tree because it's a nice, neat model to work on. What do we mean by decision tree? As the name indicates, it's a tree where at every node we are taking certain decisions. So we have essentially two types of nodes. We have decision nodes, which are starting from the root node to all the other intermediary nodes are decision nodes. And then we have leaf nodes here. So essentially at the leaf nodes, we are taking certain decisions, right? The output is a leaf node, which is in some sense a classification. For our context, we can start with a piece of code. We can have sufficient amount of data, as I indicated in the previous slide. We can have sufficient amount of data of the following kind, right? And then we are trying to ask questions. For example, for this code, for any piece of code, we can ask questions of the kind, is this code running in an expected location? For every code, we have certain expected location, right? Certain piece of code, we are expecting it to run, let's say when the machine starts. So is it running at the appropriate time? So the time at which the code is running could be a question we are asking, right? So this way we can design these decision nodes. Each decision node in some sense is capturing a particular feature or a particular aspect of my system, right? For this representation, it is binary. We have taken binary kind of a representation where the answer can be yes and no, and correspondingly we can decide in favor of leaf node 1 or leaf node 2. Similarly here, based on the decision node's output, we can decide that this is a classification if it is, let's say, true, and if it is false, then we again go to another question. We may have to ask one more question to resolve, which particular type or class this particular code belongs to, right? So this is how a decision tree works. The advantage is it's very neat. It's easy to design for somebody who has past experience. For example, we have so many experts available in the domain of security. Not only security, we can narrow it down. For example, we have people available in the context of wireless communication, security in wireless communications. So those subject matter experts have the requisite know-how to figure out what should be the decision nodes queries, right? So it's easy for them. So you need certain amount of subject matter expertise for supervised learning to design, let's say, a decision tree based solution, right? That is the advantage, or you can also view this as a disadvantage, because if you don't have domain expertise, sometimes it gets difficult to have good performance with decision trees. Another aspect of decision tree is its implementation is very efficient, because if you look at it, for those of you who come from computer science or similar background, it's like any other emery tree. So traversing the tree, we have known algorithms which are very efficient in terms of implementation. So it doesn't take a lot of computational complexity to implement a decision tree based architecture. So there is a trade-off that it is low complexity, but then you require expertise to implement it. So for example, let's say I do not have any exposure in biotechnology. If I want to implement a decision tree based solution for a problem statement in biotechnology domain, it will be very difficult for me to do, because I will not be able to evaluate are the decision nodes that I have created for my decision tree appropriate, are they asking the appropriate question? Maybe we can narrow it down to that, right? So that exposure is very important to implement an efficient version of decision tree based solution. That being said, we can further make life more interesting. So instead of decision tree, we can use something called as a random forest, which is a notch up. Again, please note, we can have classification kind of problems where effectively we are looking at a discrete set of classes. In the previous example, we had a binary class. We had malicious code and we had benign code, right? We can also have emery classes, right? From a security perspective itself, we can have maybe threat levels that, okay, is it a benign code or is it a malicious code? If it is a malicious code, is it alert level 0, level 1, level 2, right? That kind of classification can also be done, right? So we can have emery classification. Now the advantage is, in a random forest based approach, we can have emery class setup, right? A decision tree corresponding to each class, for example. And for any training data, again, I am not repeating the part of the supervised learning. So for all supervised learning models, the assumption is we have the labeled data set. We are going to use the labeled data set, train the model, generate a trained model, use it for test data. And at the time of test data, we have unseen or new data. And then we are trying to predict or we are trying to classify based on the trained model, right? So here again, I'm just going into the details of the model, but not the flow. The flow remains the same, what we started with in the couple of slides before this one. So now in random forest, what we have is, given this training data, we'll pass it to multiple decision nodes, let's say multiple class decision nodes. In this example, I have taken same for ease of representation, but you can have different structure of the decision tree itself. It need not be identical decision trees, across different classes. And at the end of it, what we do is we apply, so if it's a classification problem, then we apply something called as bagging or voting. So we can take majority logic and based on the majority logic decide which class should I, give my output at. Performance guarantees, because this is probabilistic in nature. Unlike the previous models, right? We can do some things there also, but here it is relatively easier. There is a huge amount of literature available in that direction also, right? Maybe another slide I have which will be better explaining naive Bayes classifier. So again, for this classifier, we have a binary approach, right? Which is again for ease of understanding. We can have an emery classification also. So instead of having only two classes, 0 or 1, we can have 0, 1, 2, 3, up till m classes also. And for each of those classes, I can have a distinct distribution. So in some sense, this looks like a probability, but I can operate in the probability domain based on a priori probability, or I can also operate in the likelihood domain in terms of the PDF, right? Assuming if they are equiprobable, for example, or we know the a priori probabilities, for example, right? So then I can easily obtain in either of the two domains. So here, for example, what we are saying is, if I am transmitting y, which is equal to 1, and then I am observing x. Similarly, if I am transmitting y equal to 0, and I am observing x, well, I should be saying not transmitting. Transmitting is more a language from communication, which I come from. Maybe I should be saying, if your input data is y equal to 1, or input data is y equal to 0, and we are observing x, we want to decide correctly whether y is 1 or y is 0 by observing the value of x. So what we are observing is the x-axis, the value of x, and then as you see, if I have my data as y equal to 1, I can observe across this distribution, right? And that's the randomness part, because if there is no randomness in the system, if whenever y is 1, I observe x equal to 1, and whenever y is equal to 0, I observe x equal to 0, there is nothing much to be done. We don't need machine learning in that context, right? The whole idea is there is some randomness in the system, or there is some uncertainty in the system, and we are trying to mitigate that uncertainty, trying to increase the likelihood of correctly deciding which class the particular data, or which class the particular code in terms of malicious or benign, or which class a particular node. Nodes can also be benign, and I think Professor Igor has more on that. Nodes can also be benign or malicious, right? So across our security framework, we're just trying to decide which class a particular input type belongs to. In this example, it's just binary, 1 or 0. So if, let's assume we have y hat, right, which is my prediction in some sense after observing x. Now if y hat is 1, and y was 1, then effectively it's a true positive. It was 1 and we decided correctly in favor of 1, right? We can also have false positive, where effectively y was originally 0. The data was supposed to be classified as 0, but we are wrongly classifying it as 1. So it's a false positive, where the positive and the negative comes from the legacy. So for those of you again from communication background, this goes back all the way to more than half a century or even more, where we look at these receiver operating characteristics. We have this whole theory called detection theory, and that is where this nomenclature of true positive, false negative, true negative comes from. So although we would like to believe AI ML is like 10 years old, 20 years old, no, a lot of theory that goes into these models have been around, and now is a good time to use them because we have sufficient computational complexity available. So it's easy to implement these on real world data sets. But the theory part, a lot of it, for example, this part, the whole theory behind naive Bayes classifier has been around for maybe 6, maybe more decades, close to 7, I don't know, exact dates I have to check. But that being said, coming back, so we have true positives, we have false positives. Similarly, we can have false negative, where the data was 1, but we are deciding it as 0. And we can have true negative, my apologies for the color, it's a bit dark, but this one, the blue one is true negative, where effectively the data or the node is 0, belonging to class 0, and we are correctly saying it is 0, right? Now please note here, the false positives and the false negatives are errors. True negative and true positive are correct decisions or correct detections from this naive Bayes classifier. We can also plot, just as I mentioned, the receiver operating characteristics, right? So it's exactly almost the same plot where we have probability of true positive and probability of false positive. And please note, because these probabilities are a function of the input data also, if I am never going to send or if I am never going to feed to my model y equal to 1, I can never have true positive. To have true positive, some data has to be 1. Similarly, to have true negative, some input data has to be 0 or belonging to class 0, right? And that is why, as you see here, if we keep increasing this part, the false positive probability, the the curve also saturates, right? In some sense, it's given in percentage, but you can equivalently write it in terms of probability also, right? So again, this is a nice classifier. We don't necessarily have to use Gaussian here for this particular example or illustration. It is almost like a Gaussian plot, but you can take these distributions based on the actual distribution of the data or the system. So based on the analysis we have done on a particular security framework, post observation or post running an experiment, we can come back and say, okay, if we are looking at user logins, or for example, phishing was one of the things considered yesterday, right? So if you're looking at phishing emails distribution, maybe it doesn't follow Gaussian, maybe it follows some other distribution. So you can replace the distribution, but the rest of the math remains the same. So that's the beauty of naive Bayes classifier, that you can adapt it to your system in the security context based on additional knowledge of what is the inherent underlying distribution for your data or for your nodes or for your system in general, right? So that adaptability potential is there, and correspondingly it may outperform some of the previous ones, especially as you increase the number of nodes. So one of the drawbacks with let's say a random forest or a decision tree based approach is, what if the data has a lot of features? Because in that context, if the data has maybe 10 features, 20 prominent features, decision tree would be a very good approach to use because it's efficient. You can write a piece of code, run it on an IoT device, bingo, you have IoT security, right? But imagine a security setup where there are 1,000 features or maybe 1,000,000 features, right? Or the vector size, maybe not features, maybe the vector size is 1,000,000. Then designing a decision tree or a random forest based approach becomes prohibitively costly because it's 2 to the power. If you think of it, for every input field which is independent, it's in some sense 2 to the power, unless you have domain knowledge and okay, out of the 1,000,000 I can neglect 99990, only 10 are important. Then that's a different issue. But if you do not have the domain knowledge, then implementing efficient random forest or DT based approaches become challenging, right? which is why the naive Bayes classifier comes handy, because here, as long as you have an exposure to the statistical nature of the setup, which you can do by running sufficient experiments. So if you have sufficient classified data or labeled data, then you can actually generate these distributions or approximate these distributions and then inherently try to predict or classify, right? So now, so that's naive Bayes classifier for us. And then we also have something called as support vector machine, or SVM, which is more popularly called as, where in SVM what we are trying to do is we are taking the data, any n higher n dimensional data, and we are trying to cut it into using certain hyperplanes, try to cut it into, let's say, disjoint set of classes, and then label those classes and then use this hyperplanes to decide, in some sense it's like DT, where it's operating at a hyperplane level. So for every hyperplane, in some sense, you're taking a binary decision. Is it on this side of the hyperplane or the other side? And if you have, for example, in this case, I have 3 hyperplanes, H1, H2, H3. Based on each hyperplane's outcome, we will have these regions. For example, this region. This region is below H3. Well, below is a very vague term to use, but in interest of time, and I don't want to go into the details of hyperplane, so assume this to be a 2D space, right? So for this 2D space, for H3, given the equation of H3, if any data point is below H3, to the right of H2, to the right of H1, it belongs to this region. And maybe this region belongs to benign code, for example. So it's easy to classify. However, if the data is on this side of H3 and this side of H2 and this side of H1, this is definitely malicious code. There's another way to look at it, right? In between, we are not sure. Maybe in between, there are those classes like level 0, level 1, so on and so forth, right? The advantage again for SVM is there is a lot of detail available in terms of the theory, because in some sense, this is more based on linear algebra or matrix algebra, right? So the theory part is more readily available, unlike some of the models we are going to discuss after this, let's say, for example, in deep learning context. So from that perspective, the theory is well established. And there is a reasonable trade-off in terms of implementation and performance, right? So typically, these are the 4 very commonly used supervised learning techniques that people are using when they have labeled data set available, right? Oops. Maybe I didn't. So digging a bit deeper into SVMs, so this is just an illustration of what I was talking about earlier. Please note, for this illustration, this is exactly a hyperplane cutting the green and the blue dots, right? But it's not that it has to be linear partitions only. But of course, it's easier to do it. So if you have an n-dimensional data, it's very easy to, or hopefully, not always, doesn't work all the time. You can have some blue dots with the green ones and some green dots with the blue ones also, right? So data need not be nice all the time, or the problem might not be pretty straightforward all the time. But for this illustration at least, there is a nice hyperplane and the equation of the hyperplane is available. Given this equation, it partitions the space into 2 subspaces, one subspace corresponding to the green, one subspace corresponding to the blue one, right? Now, again, we can go back to the example of benign and malicious code, right? But we can also have SVM in the context of regions which are not linear in nature. And that is where a kernel-based approach comes into picture, where we take a kernel, we try to transform the given data into, let's say, a higher dimensional space, where in the higher dimensional space, there exists a hyperplane, hopefully, which is able to partition, the region into the 2 classes, right? Again, you can take this example and you can generalize this to M class, or you can also generalize this to other setups that you have discussed so far. The beauty is this transformation is something that is non-trivial, and so essentially this transformation is a function of the kernel, right? So then the kernel is where a lot of effort goes into figuring out. So given, let's say you have data available for user logins, or you have data available for emails from your university server or your institutional servers, and now even if you have labeled data with this huge amount of dimensionality in the data, how do you decide what kind of kernel should be used? And that is where the domain expertise part comes into picture. So for example, to give an analogous example, for example, from let's say images. There is a lot of work which has happened in the context of images on what are good kernels, which can easily transform such data to a higher dimensional space where there exists a hyperplane dividing it into two classes, right? But the same need not be obvious in the context of all security based problem statements that we're trying to address, maybe potentially using SVM. So again, this choice has to come in, and I'm planning to only cover 4 for supervised learning. There exist many more, and there are variants also, by the way. I have covered only the base ones. For example, you can slightly modify the algorithm and the performance accordingly changes, right? So there is a huge amount of literature available in terms of supervised learning based models, which you can potentially explore. And each of those models has a trade-off or some plus points and some minus points also. There are no free lunches, by the way, right? So there is no one supervised learning model which always outperforms in all aspects. So there is always at least a trade-off between complexity and performance, if nothing else. So if there is a very good model which is performing exceptionally well, it will maybe take significant amount of computational complexity. Because if there was a model, let's say one numero model for supervised learning, we would not be discussing all of this, right? We would be studying only that model, which works all the time. So but that's not true, because there is a trade-off, right? So based on the trade-off, you need to choose. So based on the question you're trying to answer in the context of application of machine learning in the security domain, you need to decide, are you going to run this algorithm in the cloud? Are you going to run this algorithm at the edge device? Are you going to run this algorithm in the IoT device? And correspondingly, the computational complexity resource you have available, it goes up or down. So that's one parameter you have to look at. Memory could be another. Time taken or time required to run it could be another. Maybe there are ML-based classifications which have to be done now before this interrupt or before the next interrupt occurs. So then you can't, even though you have cloud resources available, you may not have time to send the data to the cloud and wait for a classification result to come back. So latency could be another issue. And then based on these constraints on the system, we might have to choose which kind of model might be better for us. We should also be exploring, in certain scenarios, it may not even be good to use any of these. Maybe a heuristic based approach turns out to be better. It satisfies more of our constraints than any ML model. And that is why, although a lot of buzz is there around AI and ML across the globe, there are still a lot of systems which are not, a lot of practical systems which are not using any AI or ML. For the sheer reason that they work, they don't need to use. Same is true for security also. So we also have to think, do we even need such an algorithm to solve this particular problem statement that we're trying to solve in the context of security, right? That being said, let's come back. So let's just summarize quickly supervised learning based techniques. So we can have SVM, naive Bayes classifier, decision tree, random forest, and we can use them to solve problems, for example, of the kind malware detection or intrusion prevention, phishing protection, user behavior analysis. Again, these are not an exhaustive set, because already in yesterday's introduction session, Professor Igor covered superset, I should be saying. So I just put some there for illustration. But the understanding is we can use them as long as labeled dataset is available. There are also these requirements in terms of how much data is available. So if you have 2 samples, one benign and one malicious, maybe that will not be enough, right? So each of these models, that is another aspect you have to look at, how much data you have available for training that can give you a well-trained model, which can then try to predict or classify in the testing phase, right? So that was all that I wanted to share about supervised learning. Let me quickly jump on to unsupervised learning techniques. So one key difference between supervised and unsupervised learning is, in unsupervised learning, as the name indicates, there is no labeled data set available. Data is there, but the labels are not there. So we have the piece of code. We may have more codes available. So let's assume we had a million set of codes for supervised learning techniques. Maybe we have 10 million now, but there is no label. And this is again practically very much possible, because a lot of times new codes that we see, or new nodes that enter the system, or new users that are logging in into the network, they do not have any label attached to them because they are new. How do you label a new user? If I have sent you an email and I am sending it to you for the first time, how do you know the attachment is benign or the attachment is malicious? But of course, it's better to be cautious. As Professor Eva was mentioning, if you're getting something from the defense, highly likely, if you do not have any direct contact with them, maybe it's a malicious piece of email. But that kind of awareness may not be there. Please also note, folks in this session are in some sense privileged because you have that kind of background. Most of you are coming from technical background, right? So you have that kind of awareness available that, okay, if I see, some poker.com, you have won ₹1 million, open the PDF, enter your Aadhaar detail, this, that, 99.9% this is fake, right? But please note the access to email is available in the Indian context to 90% plus population now. Everybody has a smartphone. Every smartphone has an option of email. So this challenge of unlabeled data reaching users and then somehow tackling it at that level itself becomes really prominent, and it scales very fast, right? Coming back to the unsupervised learning techniques, so here we are assuming significantly or reasonably large amount of data is available, but the data doesn't have labels. Without the labels, we want to use some supervised learning techniques or some supervised learning models and then try to classify or try to create the classes themselves. For example, we can use it to detect novel threats or to detect novel anomalies in the system, right, from a security perspective. How to do that? Again, there are a couple of algorithms. I'll be touching upon very few of them, but then there is a huge amount of networks available. For example, I'll not even be touching on networks today because then we'll be digressing a lot and I will be eating up the whole session on networks only. But maybe the easiest one first. So K-means clustering. What is K-means clustering? In K-means clustering, for example, we can use a centroid-based approach. What do I mean by centroid-based approach? We have a lot of data. Let's say the red, green and the blue dots is data. And now I want to create clusters. In this particular example, 3 clusters. One way to create clusters is each of those clusters should have a centroid such that if I take the distance of each of the point belonging to a particular cluster from the centroid, this variance in some sense should be minimized with respect to the centroid, right? Or the point should be closest to that particular cluster's centroid, right? That's a centroid-based approach we can use. You can also view this as the error in some sense. The error should be minimized post classification or post clustering. And as the figure indicates, here we have 3 such tessellations. You can also view these as Voronoi tessellations in some sense because they are distance based. So this tessellation or this region belongs to red, this region belongs to blue, this region belongs to green. And the beauty is we didn't have the label. This clustering is being done purely on a distance based metric, right? But then an important aspect is there has to be a notion of the distance also on the data. So if, for example, let's say you have emails and now it's just emails, right? We are not even going into the attachment part. If you have the email data, the body of the email, the address of the email, now how do I define distance on such data, right? And that is where experience comes into picture based on how you have tackled such problems with a particular type of data. For example, for images it is easier because in the context of images, these are values, RGB values, right? So these are, let's say 0 to 256 or 0 to 255 each. It's a vector of size 3 for RGB. So then you can still very easily define a notion of distance. But now we are talking about emails, phishing emails. So how do I define a notion of distance on top? So it's not very straightforward, right? So it's not that all of a sudden I can one day say now I'll use K-means clustering and use a K-means clustering based approach for creating classes across the types of emails that I'm getting, right? But that being said, there are sufficient types of problems where it should be easily possible to apply this in the context of security also. We need not always have a centroid based approach. We can also have a model based approach. For example, if you recall supervised learning technique, naive based was based on the statistical aspect or the distribution of the data itself. So similarly here, let's say we have some know-how that we don't want to use a distance-based approach. We have a know-how that there are classes, and those classes are because in the experiment or because in the security setup, there is a distribution being followed by certain classes. Maybe those distributions are Gaussian. So then effectively you can view this as a plane where the Gaussian is a 2D Gaussian sitting on top of this XY plane, right? And that is why we have now this circles or kind of like circles, unlike the previous k-mean clustering based approach, right? We can also have density based clustering, and there are several models there. I will not go into detail of each one of them, but the difference between density based and model or k-means clustering based approach is k-means clustering is just distance based. You're taking centralized based approach. Similarly, in model based, you're assuming there is an underlying distribution for different classes. But either of them does not capture density. So it can so happen, and you can create those counter examples also with data, that there are locations which are denser. For example, this one, as you see here, this is a dense set of data, the blue one, and the green one is another dense set of data. So highly likely they belong to two different classes. But if you use a k-mean clustering based approach on this is not the solution we are going to get. Maybe what we'll get is some sort of a tessellation, cutting across either the green or the blue. So part of the data will be either becoming false positive from our previous nomenclature perspective if you want to use it, or it will become false negative, right, with respect to that particular class. So there are models like DBSCAN, and then optics is a more recent variant which do this job very well, and which can be used again. For example, we were discussing denial of service attack, right? So now what is the amount of frequency of attack, which location is it coming from? Can we use that information, or can we use just the login information without even knowing whether it is a DOS attack or not? And just a density based approach can also tell us if it's a DOS attack going to happen, it will be denser compared to all the other users which are normal or benign users, right? So you don't need any sophisticated technique to trigger occurrence of a DOS attack, right? But that being said, we can also have, let's say, PCA. Again, this is supposed to be a GIF, but this is similar to SVM for unsupervised learning, where we are taking data, we are trying to represent data in a particular domain, we're trying to find the principal components, and then along those, in some sense, we're trying to divide the region and divide into two classes, right? Can be done for other setups also, right? It would have been nice if it displayed, but nevertheless, in interest of time, I think because I have more things to cover, I'll go on to a summary for unsupervised learning technique. So one of the key use cases for unsupervised learning technique is anomaly detection, because for anomaly, please note the underlying assumption is it's not a known anomaly, because if it's a known anomaly, you will be using a supervised learning technique. We are trying to detect new anomalies in the system. So how to do that? There is no label available for a new anomaly. One way to do that is to use unsupervised based technique, where, for example, we can use it to detect unusual behavior in the system. We can use it to detect, uncover hidden threats, or identify new attack vectors, and then combine all of them together through a k-means or a PCA based approach to say, oh, there is some anomaly happening in the system. But there are a couple of challenges with this approach. One, it still requires an SME. There has to be a subject matter expert, because let's say the system says this particular user is or this particular scenario there is an anomaly, but how do we know for sure? Who will decide? There has to be a decision made, right? And for live systems, for example, let's say an IoT system for surveillance cameras, for traffic signals, we can't stop the feed or we can't change the direction of the camera just because an unsupervised learning technique says, no, this is beyond the cluster of regular benign nodes. This appears to be an anomalous node. Do something about it. Somebody has to make that call, right? Some subject matter expert has to make that call, and this has to be done on a continuous basis. It's not that once we do it, today if an anomaly is detected based on k-means clustering based approach, then done. No, tomorrow if there's a new anomaly being detected, again somebody has to go through that log. Somebody has to cross verify, is it a correct decision being made or not, right? So that ways you require that SME component, subject matter expertise component, to ensure this works well, in field. Although it is very easy to implement it, the algorithm is available, you take any data, you apply the algorithm, it will give you some result. But is the result correct? How do we know? Right. So that's one of the challenges we face in the context of unsupervised learning technique in the domain of security. Coming to the other two, if you recall the first slide, there were 4: supervised, unsupervised, dynamic or reinforcement learning, and deep learning, right? This is the one I'm going to spend the least amount of time on. So reinforcement learning is a dynamic learning technique where effectively what we have is we have these agents. These agents, they perform certain action dynamically with respect to time, for example. Time is just one dimension, you can have other dimensions also. So based on this action, the environment, it has certain reward, can be positive, can be negative. You can also view this as a feedback. For those of you who are from control system background, there is nothing but feedback. So it's a closed loop feedback, and based on the feedback, the agent again decides, should I perform the same action or should I perform something else? But please note, the agent is doing two things, not parallelly. The agent is either exploring the system or the agent is exploiting the system. What do you mean by exploring and exploiting? In the exploration phase, the agent is just checking, if I perform this action, what happens to the environment? What is its state? It keeps on sensing, and then basis this, it decides, okay, if this is the state of the environment, maybe if I take this particular action, this is the kind of reward I'm going to get. And the reward is the exploitation phase, because for that amount of duration, let's assume time as our dimension for now, or the basis for now. So for certain amount of time, when we are exploiting the system, we are just trying to extract out the reward based on our actions as an agent. But then the environment can change, and that is why we are talking about reinforcement learning from a dynamic learning perspective. Think of it as, let's say, the phishing example that we are discussing, right? We have a model, the model trains on input emails, and it decides whether a particular email is malicious or not. Based on this decision, you open the email, you allow the user to open the email, and then if nothing happens, hopefully it was a non-malicious email. Because please note, attackers are smart folks, right? It's not that all attackers will send a file which immediately will hack your system. No. Maybe they will send a file which will wait for 10 days, n number of random days, and then it will start slowly capturing control over your setup, and then something may happen. So this immediate state or immediate reward also may not directly have a connotation from a security perspective. So we keep doing it. We keep running the setup, and then continuously we decide what fraction of the time we want to explore, what fraction of the time we want to exploit. Again, this is a trade-off which has to be chosen. Now, those of you who have worked on these models, there are these parameters. For example, Q-learning based model, you will have this parameter, which you will tune. Again, that comes from exposure. From a security perspective, you need a lot of exposure with that kind of problem statement to decide for this particular environment, how much should be my exploration phase, how much should be my exploitation phase, right? But that being said, there are a lot of use cases where reinforcement learning comes very handy. For example, intrusion detection systems, intrusion prevention systems, in the context of IoT, because it's all dynamic in nature, there's a lot of sensing happening real time. Identity and access management, because again, users are coming, users are logging in, users are logging out. For example, for this particular workshop, users are logging into our IETH network, for example, those of you who are present here, right? So dynamically you are connecting to the network, and then you are going back, and then again you are coming. So given any setup or environment where there is time varying nature in terms of the data, time varying nature in terms of the nodes, reinforcement learning or dynamic learning turns out to be a better approach than unsupervised or supervised, right? We can also combine them, by the way. I'll come to that part also subsequently in a couple of slides. So now, so I'm purposely not spending a lot of time on reinforcement learning because I want to spend some more time on, let's say, deep reinforcement learning or double deep reinforcement learning, where there is more state of the art, right? So coming to the fourth one, which is deep learning. What is deep learning? So in deep learning, we can have, again, I'm going to explain through CNN, but you can have other approaches also. What is a CNN based approach or a convolutional neural network based approach? As you see here, let's say for a particular input image, you perform some convolution here on this image and you get some feature maps, and then you again perform subsampling and convolution, and this way you are reducing the dimension in some sense. And now we are trying to figure out at the output layer which of these are relevant for us, and then we can have a layer sitting here connecting this, a fully connected layer sitting here connecting this subsampled version to the output, where output is in some sense the labels of the classes. For our example, if you go back, maybe it's a binary output. Is it a benign piece of code or a malicious piece of code, right? But then you can have more involved examples also, even in the context of security. Now please note, as I was talking about naive Bayes algorithm, CNNs have been around. It's not that CNN is a 5-year-old, 10-year-old technology. CNNs have been around for a lot of time, a couple of decades if I'm not wrong. But then the challenge was, in the context of CNN, the computational complexity was one limitation, right? Because here we don't do it in practice, but theoretically you can have interconnections from each of the pixels of the image to every point in the next layer, theoretically, if it's a fully connected setup, right? Then it exponentially scales with each layer. Now if you take an image of the size 1024, 1024, which is not a very good size, by the way. If you're using a 4K phone, you already have images of much higher resolution in your phone, right? But given even 1024 cross 1024, we are effectively looking at 2 to the power 20 bits, assuming monochrome images, right? Now imagine for each layer, if it's going to exponentially scale it to the power 20, it is not computationally possible to compute it even now, right? Even with our current nice GPU based architectures, it's difficult to compute it. So what has changed? One thing that has changed in the setup is people have realized we don't need to have interconnections, we don't need to have fully connected layers at all the phases of the CNN. What we can do is we can only pick and choose the prominent ones, and then that is where the training part comes into picture. We can pick and choose the important ones and neglect things which are not relevant. And we can do this iteration through backpropagation and other things. So effectively we can optimize the CNN if we have, let's say, a labeled data set available. So it is kind of like supervised learning, but using neural networks, right? Again, because of the complexity of the model itself, because it's neural networks, right? So there are interconnections between those neural net. So if we do not have sufficient amount of data, it is very difficult to train such CNNs. So that's one of the challenges we face. Unlike DT, for example, DT is the most straightforward. If you know the system, DT is probably where you should start, because you already know the system, you know what questions to ask. You just have to transform those questions from a security perspective into a decision tree's decision nodes, right? And job done, half the job done. But for CNN, you need the label data, and you need sufficient amount of label data. Otherwise, that notion of interconnections being there, maybe wrong interconnections will still persist in the system if you don't have sufficient data. And then when you use it in the testing phase, it will incorrectly classify a benign code as malicious or a malicious code as a benign code if it's a new code, right? So it's very important. The data size for training part is very important in the context of CNNs. Again, this is just an illustration, but to give you an idea, for example, let's say this is from an image perspective, but we can redo this for a code, we can redo this for a network, we can redo this for a packet in the network. So again, we can repackage the same thing from a security perspective also. But then these are more commonly used examples. So let's say we have LeNet and LXNet, and in more recent times we have ResNet and UNet and all. Again, so you can have maybe a 5-day session only on CNNs, right? Or if you just go through all the models, the intricacies and the trade-offs and all, right? But for us, what is more important is to understand that given this input, we are trying to transform it using some kernel and performing a convolution with this kernel into, in some sense, a tensor. We are re-representing the data, right? Once we have re-represented the data, with a pooling layer and a convolution layer, we are downsampling it, and then we are downsampling it to the extent that we are reaching a point where only important stuff remains. Rest, noise, we should be removing from the system. And this is not done manually, by the way, and that is why large amount of data is important, because if we do not have good amount of, well, I shouldn't be saying only large, good data. That is where the data part becomes very important, because if the data is not having sufficient variety, if the data is not sufficiently large, then this downsampling which is happening in some sense may happen in an erroneous fashion. So although CNNs work, but they work under certain constraints, right? And then we can also have recurrent neural networks. What is different between an RNN or a CNN? In a CNN, there is no possibility of switching the state externally of the neural network. Whereas in a recurrent neural network, based on the training, we can also decide whether we want to use, so this is the input part. This is one particular, you can view this as a node inside the network. So for this node, you can actually choose which weight to consider, or maybe this CT part will be better to explain. So using CT, we can choose whether you want to use CT or you want to bypass it in some sense, right? And the advantage is now the network has memory, and that's why the name. So for example, one type very commonly used recurrent neural network is LSTM, or long short-term memory, where now I can, based on my training, I can now choose if a new data input comes, whether I should be using the weights or whether I should be neglecting the weights or a particular node, right? Which is very important, especially for data where you have certain amount of memory, in the sense that, let's say a video is nothing but a collection of images, right, with timestamps attached to it, and it can have correlations also. For example, for the recorded session that we are having, it is essentially a set of images. In one image my hand is here, then it's moving gradually across the images, right? So there is a correlation existing between those images. Now if I'm going to use this video for any prediction, any classification task, because inherently there is correlation in the data, I should be exploiting that temporal nature, that correlation of the data from a temporal perspective also, which is not possible in a CNN. Because for a CNN, you have to parse the whole data. Either you parse an image or you parse the whole video.